Alright, so welcome back. This is our last video in Unit 3, talking about the idea of graphing our rational functions. So in graphing the rational functions, there's three different concepts that we're going to have to identify. The asymptotes, intercepts, and any holes in the graph. Asymptotes can be vertical on either horizontal or oblique. Intercepts can be the x and y, and obviously the hole is just simply a hole in the graph. So as far as the asymptote goes, the horizontal asymptotes is the value the rational function's approaching on the extreme left and right sides of the graph. This value will depend on the relative degree of the polynomials in the numerator and the denominator of the function, whether or not it's a value like 0, a non-zero number, or something that's more like infinity. So if the degree is greater in the numerator, the degree in the denominator is greater than the degree in the numerator, then horizontal is always 0. If the degrees are the same, it's then going to be the ratio of the leading coefficients. And if the degree is greater in the numerator, then you're creating what's called an oblique asymptote rather than a horizontal asymptote. And obliques are either slanted or curved lines that describe the direction the rational function is on the extreme ends of the function, which we'll use either long or synthetic division to find, depending upon how the function is set up. So we want to find the different examples for this one right here. So we recognize A, the greatest exponent is in the denominator, so our horizontal asymptote would be y equals 0. For B, the greatest exponent is the same top and bottom, they're both x squared, so it's the ratio of negative 6 over 3, which is negative 2. And then finally, that last option, we can see the greatest exponent's in the numerator. So this is set up to find an oblique asymptote, not a horizontal. And because we are dividing by linear expression with coefficient of 1, we can do our synthetic division to solve this problem. Putting a 2 on the outside, 3, negative 9, and 2. And when working through this synthetic division, we're not going to need to worry about what the remainder is. This part right here tells the oblique asymptotes. My oblique asymptote is the equation y equals 3x minus 3. Alright, so that's how we can find the horizontal or oblique asymptotes for graph. And we're going to kind of do this for each of the other concepts first, kind of show how we're going to find these things, the vertical asymptote, intercepts, all that kind of stuff, holes, and then we'll take a look at a couple graphs illustrating each of these concepts. So the vertical asymptote, this is what happens when we are dividing by 0, because we're not allowed to divide by 0. So what we're going to do is we're going to factor the denominator and solve it, though if there is a factor in the numerator that cancels with the factor in the denominator, that's going to create a hole instead of a vertical asymptote. So if we have this expression right here, we factor the numerator as x minus 4 and x plus 3. Factor the denominator as x minus 4 and x plus 4. So the x minus 4 is cancelled, so this tells me there's going to be a hole in this function at x equals 4, the solution of the factor. It's not what we're talking about right now. We're only talking about the vertical asymptote, which is then this. So our vertical asymptote would occur at negative 4. The numerator is not relevant towards the vertical asymptotes, so we don't need to worry about that for that. However, the numerator is relevant for the x-intercept. So again, like with finding the vertical asymptote, we're factoring the numerator and denominator. If something cancels, it's a whole rather than an x-intercept, but whatever's left over, the solution of the numerator will be the x-intercept. It's possible that there's nothing left over up top. So then there might not be any x-intercepts in the entire problem. And as far as the y-intercept goes, we're just setting x equal to 0 and solving for y. It's always rather straightforward. So we have this function right here. We want to find our x and y-intercepts. So again, we are factoring. So this becomes x plus 9 and x minus 2 up top. X minus 2, x plus 2 on the bottom. So the x minus 2's cancel. So our x-intercept would only occur at negative 9, because that's the x plus 9 expression left over. As for our y-intercept, this is now where we substitute 0 in for x. So we'd have 0 squared plus 7 times 0 minus 18 over 0 squared minus 4. Negative 18 over negative 4 reduces to 9 halves. So we'd have y equals 9 halves for our y-intercepts. In terms of graphing it, we would recognize that 9 halves is the same thing as 4.5, which makes it easier to actually plot. Okay, so factoring is pretty much going to be the very first thing you're going to do once you've identified your horizontal or oblique asymptote scenario for the problem. You're going to factor it because then the numerator tells you the x-intercept, the denominator tells you the vertical asymptote, and things that cancel tell you the whole. And not all rational functions have a whole, but this just simply occurs when the numerator and denominator are both going to cancel out in some way. The x-coordinate of the whole is the solution of that factor, and then the y-coordinate is when we substitute that x value back into the reduced form of the rational function, what we get left over. Again, it has to be the reduced form though. If we try substituting back into the original rational function, you're going to get a value of 0 divided by 0. And that's not ideal, so we're not going to want that scenario. Alright, so we have this function right here that we're going to try and factor to find our whole. You'll need to use your AC method of factoring or guessing and checking, kind of your choice here. So we're going to find this top is going to factor as 3x minus 2 and x plus 5. The bottom will be an x minus 2 times x plus 5. So we can clearly see the x plus 5's canceling. It leaves 3x minus 2 over x minus 2 behind. And then as for our whole, because something canceled, the x-coordinate of the whole is going to be at negative 5. So for the y value, we're going to substitute negative 5 into the problem. So it's 3 times negative 5 minus 2 over negative 5 minus 2. We get negative 15 minus 2 over negative 7. Negative 17 over negative 7, which then the negatives reduce into 17 over 7. So our whole would occur at negative 5 comma 17 over 7. All right, so now what we've done the past four examples here, we're going to put it all together now for one problem and also sketch the graph at the same time. So for this function right here, again, we're graphing it. So in order to graph, we need to find the horizontal asymptote, which we can recognize since the greatest exponents in the denominator will occur at y equals 0. As far as vertical asymptote, x-intercept, y-intercept, and whole, we're going to want to factor this expression. Top doesn't factor at all. Bottom does, is x plus 5 and x minus 1. So nothing cancels, so there will be no whole for this graph. The vertical asymptote will have two locations, negative 5 and positive 1. From the two solutions in the bottom, x plus 5 and x minus 1. Our x-intercept would occur at x equals 2, the solution of the numerator. Our y-intercept, we go ahead and substitute 0 in for y. You'll find it's 2/5 because you just get negative 2 over negative 5, which is a positive 2/5. And again, the whole, there is none because nothing canceled. So now putting it all together in terms of our graph. So we do a dotted horizontal line at 0, which is the x-axis. Now you might not be able to see it too well when you're doing it on your own with pencil over top black versus my red mark there over top this, but just do the best you can to show the horizontal asymptote there. We then do vertical asymptotes at negative 5 and at positive 1. We plot the x-intercept at a positive 2. You'll find that we are allowed to cross the horizontal asymptote. That is perfectly allowed. What's not allowed is crossing the vertical asymptote. But because the horizontal asymptote talks about what's happening at the extreme end, we're allowed to cross in the middle. We then plot the 2/5, and that's all we have. Now, when it comes to making the graph, you can also plot more points and find more values. We pretty much have three regions to worry about. The region before negative 5, what's happening there. The region in between negative 5 and 1, what's happening there. And the region after 1, what's happening there. And we could plug in more points, so like a negative 3, negative 7, positive 3, positive 5, like a whole bunch more points to find actual locations. But the idea is making a sketch. And we can use a little bit of logic for certain stuff. For example, the middle section, we have a point, our y-intercept, clearly above the x-axis. And we're only allowed to cross the x-axis at x-intercepts. Well, there are no x-intercepts in that region, which tells me my entire curve should stay above the x-axis. Since I can't cross the vertical asymptotes, I'm going to create a graph that kind of looks like this right here. So that's my middle section. And along a vertical asymptote, you'll typically find that the curve goes in opposite directions. On one side it will go up, on the other side it will go down. The only time it ever goes in the same direction would be if the vertical asymptote came from an expression being squared. So like for example, if this was x plus 5 squared, in the denominator rather than just simply x plus 5, my vertical asymptote would go up in the same direction along negative 5 on both sides there. But since it's not being squared, they're going to go in opposite directions. So it's going to come from below. And again, I can't hit the x-axis because I don't have an x-intercept there. So it just kind of flans off along the x-axis. It's also going to flatten off along the x-axis because that's where the horizontal asymptote is. And the extreme end left and right side has to be flat along the x. So here on the side of 1, same thing. I went up on the left side of 1, so it has to come from below on the right side of 1. This time I am able to hit the x-intercept, but I can kind of just stay above it a little bit and then drop along the x-axis there. And there's our sketch. You would find if you were to substitute values in for -4, -3, -2, and -1, they would all be positive values above the x-axis. Same thing plugging like 3, 4, 5, 6, and so on. Be all positive values. And on the other side, -6, -7, -8, -9, -10 would all create negative values. And again, it's not necessary to do that for the sketch. You can apply basic logic for where the points actually are on how the curve is supposed to go. All right, so that's an example of a horizontal asymptote at 0. Let's do another example. This one now we notice the exponents have the same power top and bottom. So therefore, our horizontal asymptote is going to occur at 2, the ratio of the leading coefficients. For our vertical asymptote, we still need to factor and solve this. We do recognize that there is a 2 in common everywhere up top. So it becomes x squared minus 2x minus 8 for that, which will make factoring easier. It's 2 times x minus 4 and x plus 2. The bottom is x minus 4 and x plus 3, and now we'll notice something cancels. Our reduced form would be 2 times x plus 2 over x plus 3. This tells me that there is now a hole at the graph, hole at 4. There's only one vertical asymptote. It's occurring at the solution of x plus 3, which is -3. There's only one x-intercept. It's solving at x plus 2, means we have x-intercept at -2. Our y-intercept, if we substitute 0 in for x, we're going to get a -16 over -12, which is going to reduce to 4 over 3. And as for our hole, well, we obviously have it at 4, and then the y-coordinate is plugging 4 back in now the reduced form. So it'll be 2 times 4 plus 2 over 4 plus 3. We get 2 times 6 over 7, which is 12 sevenths. Which is bigger than 1 but less than 2 for when we plot this. And again, it's always the reduced form you have to plug in your hole to be able to do it correctly. All right, so this time the horizontal asymptote's at 2. So we do our dotted line at 2. Vertical at -3. So we do our vertical dotted line at -3. X-intercept at -2. Y-intercept at 4/3, so it's a little bit above 1. Hole is at 4/12, so it's above 1 as well. We'll do a hole there. So now, graphing this particular rational function, we see that there are 2 regions. And again, each region is split by the vertical asymptote. So if there's only one vertical asymptote, there's only one region. So our 2 regions are before -3 and after -3. Now, after it, we see that all those points are operating below the horizontal asymptotes, which tells you my curve is coming from below, hitting those points, and then kind of running along my vertical asymptote, my horizontal asymptotes. Whereas on the other side, logically, again, it has to run along the horizontal asymptotes. There is no x-intercept, so it can't go down to cross the x-axis. And since at -3 on the right side it came from below, I need to come from above on the left side of it. And my curve looks like that. Again, if you're not 100% confident that's how the curve should go for the left-hand side, substitute -4, -5, -6, whatever you want into the function and see what do you get. You'll find values that are above 2, and you can kind of plot them out and kind of make your shape in that kind of way. All right, so we did an example where the horizontal asymptote at 0. This one was at a non-zero number. We also then have our oblique asymptote scenario. That's what we have going on here. So to find the oblique asymptote, we do need to use our synthetic division. So it'd be a 2 on the outside, 3, -9, and -12 on the inside. So we get -3, -6, -15. But again, the 3 and the negative 3 is what's relevant, our oblique would be at y equals 3x minus 3. We do need to factor this to find our vertical and x-intercept, so we can take the 3 out. It's x squared minus 3x minus 4, which factors as x minus 4 and x plus 1. The bottom doesn't factor, and we see nothing cancels, so there are no holes in this graph. Oops, not HA, it's VA. Vertical asymptotes at 2. X-intercept, there's 2 of them at 4 and negative 1. Y-intercept, if we substitute 0 in for x, you just get negative 12 over negative 2, which is a positive 6. And again, there is no hole because nothing canceled. Now I'm going to do the oblique asymptote last because it's going to be a little interesting to plot that one out. So we can see our vertical asymptote occurring at 2. X-intercept at 4 and negative 1. Y-intercept at 6. Now, the oblique asymptote is just going to be the dotted line that goes through the equation y equals 3x minus 3. I'm going to do that in blue so we don't confuse it with the different points. So we're going to start at negative 3, and we're going to go up 3 over 1. And if you have a ruler, then you can do this with a perfectly straight line. Otherwise, you should continue the pattern and go through the entire graph as best you can. And then I'll just connect them back with the red dotted line. And there's our curve there. So we still have our 2 different regions, to the left of the vertical asymptote and to the right of it. But now our curve is going along the oblique asymptote in addition to going up along or down along the vertical asymptotes. So we do need to have it running along the oblique. So we start running along the oblique. We hit our points. We're going to keep on going up. On the other side, because we went up along the vertical, we're coming from below along the vertical. Hit our point, and then we're going up along the oblique as well. So our oblique asymptote graphs can look a little weird, especially if the slope of the oblique asymptote is a 3. If the slope is a 1, it would probably look a little more normal for this kind of function. But that's going to be the general idea. You're going to see it's going slanted line in the problem. You're going along the slant is along the vertical as well. All right, well, that's it for our graphing rational functions. That's actually it for our rational functions in general. So again, feel free to look back at any of those other previous videos. Anything at all from Unit 3 if you're having issues with the adding, subtracting, multiplying, dividing, simplifying, solving, word problems, or these graphs here with 3.6. All right, so I'll see you everyone next time with Unit 4.